Untitled
So let's check out average velocity. Let's read the question. Under what condition is the average velocity defined to be the total displacement divided by the time equal to the average of the initial and final velocities, vi plus vf over 2? So here's what the question is asking. When is my average velocity, v with the bar on top, equal to the average of my initial and final velocities, vi plus vf over 2? Now, I used to get confused by this a lot, right? I thought these two were always equal. Otherwise, why would you call it average velocity if you weren't literally taking the average of the initial and final velocities? Turns out this is not always the case. This is true only under certain conditions, and we're going to find out which conditions. Let's draw some graphs to clear up any misconceptions. This is a VT graph, and let's say you start at some arbitrary velocity v0, and you travel up to some arbitrary time t. Well, what's your velocity? What's your average velocity? Your average velocity is your total distance over time. Well, what's your distance? Your distance is going to be the area under this velocity graph. How do you find that area? How do you find the area under this velocity graph? Well, the area under this graph can be found by chopping it up into pieces you know. What's the area of this piece? Well, it's simply base times height, so v naught t. What's the area of this piece? Well, it's simply a triangle, right? And a triangle's area is half my base times my height. Now you got to be careful here. The height, you end at what? Your ending velocity is vf, v final, your final velocity. So that's going to be vf, but don't stop there because you only want this height. You don't want the whole thing. So you have to subtract out this much, which is v naught. Okay, so let's take that out. So I'm going to subtract v naught from this. And now we can find the total distance by just adding these up. So my total distance is going to be v naught t, which comes from here, plus half t times vf minus v naught, which comes from here. So let's add them up. What do we get? I'm going to get divided by t, of course. What am I going to get? Let's see. On the top, I have v naught t plus half vf t minus half v naught t, all divided by t. So what's that going to equal? Well, all the t's cancel out. Notice that. All those t's cancel out, which is what we want, of course. And what do we have remaining? Well, we have v naught plus half vf minus half v naught. So what's that going to give us? Well, I'm going to have v naught minus half v naught. That's just going to give me half v naught. And I'm going to add that to half vf. And so what am I left with? My average velocity is equal to half v naught plus vf, right? And so that's what you would traditionally expect, right? We just proved that average velocity is equal to half of the initial and final velocity. But that's not always the case. To understand why, let's draw a kind of limiting edge case, shall we? So let me go down here. Let's draw something. Let's draw a VT graph where the average velocity is not the average of the initial and final velocities. So let's try a super weird graph where the acceleration is definitely not constant, but you still end at some time t. Okay, so you still end at some time t. And so what's my average velocity going to look like? Well, if you follow the traditional formula, which tells you to find this average of the initial and final, here's my initial, here's my final. That tells me that this is my average velocity, vi plus vf over 2. But check it out. The distance traveled under this velocity is much greater than the distance I've actually traveled. Check it out. The distances, the areas under the curve, are nowhere near the same. And so this is a case where the average velocity is not working. where it fails to show that the average velocity is the average of the initial and final. Now you might conjecture that's just because the acceleration is not constant, and that is partially true. But there are cases where the acceleration is not constant and this formula still holds. For example, let's check out one such case. If I have a graph like this, check out what my initial are, my final velocity are, and what's my average velocity going to be? Well, it's going to be like that, right? And now, if I actually plot my average velocity, what happens? This is my average velocity, right? This is my initial, and this, of course, is my final. And so what's the area under this curve going to be? Well, notice that it's the same as the area under my graph, right? The area under this whole thing is equal to the area under this whole thing, okay? So that's why the average velocity formula works, even though this is not a case of constant acceleration. So, in other words, the area under this green constant curve is the same as the area under this curve. And you might ask why? Well, check it out. This green curve, this green constant curve, it accommodates this, but it misses out on this. Whereas my actual curve, it accommodates this area, but it misses out on this area. And so at the end of the day, it all evens out. And so what are we left with? Let's check out the answer choices. Oh, that's the last question. Let's check out the answer choices. The average acceleration must be constant. Now, that's not true. We just saw a case where the average acceleration is not constant, and we still have this formula being true. So A cannot be the answer. The acceleration does not have to be constant for the average velocity formula to be true. It is true for other motions beside constant acceleration, but not for all possible motions. Yes, that's the correct answer. It's a very nuanced thing. The average velocity formula works for all cases where the acceleration is constant, but it also works for some cases where the acceleration is not constant. And so that's the results I leave you with for today, and that's a good place to stop.
Ambition plus MKO plus scaffolding equal learning. We believe anyone can learn anything. That's why our motto is memorization is a crime. And that's why we partnered with Brilliant.
Brilliant transforms math and science into hands-on activities so that you too can understand everything from first grade math to E equals MC squared. Barry Science Lab and Brilliant is your MKO and will give you the scaffolding to expand your ZPD until you become the next Sir Isaac Newton or Albert Einstein.
Visit brilliant.org/Barry Science Lab today. And the first 50 of you to use that link will get a 20% discount on the Brilliant annual subscription.
Don't forget that you too can become the next Einstein. So let's fall in love with math and science.